small thing. It's ridiculous.
Oh, so that's the new method with
Yeah,
no,
this-
no error, no anything.
Yeah, it only has the, well, it has a head, this one at least has a headband back.
Yeah, okay.
And I feel like I got the new iPhone 7 and a new Mac, and I feel like now I have 1,000 dongles.
Okay.
Have any of you looked at the videos on YouTube? Did they look okay? Can you, do they decipher all the sound okay?
Yeah.
Okay, does you can read the blackboard all right?
Yeah.
iPhone 7, not it's a great camera. Phone, not so much. Another minute or two and then we'll get started. So in this lecture, we're going to bring together some of the pieces from the first and the second lecture and talk about second kind equations. I'll tell you a little bit about these two types of equations, but the end of this is going to be a numerical method that uses the Gauss quadrature that we talked about last time to solve integral equations in 2D. It's a very effective technique, very widely used in practice, but also difficult to extend to 3 dimensions. So It isn't the only topic we talk about, but it is certainly an important one, and it's such an effective method in 2D. It's good that you know about it, even though many of are probably dealing with structures for which 2D doesn't really make a lot of physical sense. Dragon F14, for example. And I'm just going to remind you, in 2D, one of the things that makes it difficult to get a handle on the physical insight is the 2D problem means it's infinite in the third dimension, and that means the Green's function you're familiar with, that the potential produced by a point charge dies like 1 over the distance, turns into this log function, which of course doesn't do what you expect it to far away and nearby, but it is the way you get for the Green's function and what goes in the integral when we talk about calculating the potentials from densities. We're thinking about the densities. It looks like points in the 2D space, but in 3 dimensions it means each point corresponds to a infinitely long integral charge. So we're going to talk a little bit about these 2D problems in particular. We're going to say a little bit about, I'm just going to remind you, how we discretize, or one of the ways we talk about discretizing in 2D, and then by the end of this lecture, we're going to completely abandon this approach, even though we'll come back to it when we talk about 3D problems. So the idea was, if you're doing 2D problems, then your surface for the 2D problem, remember we're imagining in the 2D problem that we have Laplace equation outside. The Laplacian of the potential outside is equal to 0. We have a boundary condition, u in infinity goes to 0. And I apologize for the blinking. It keeps on persisting. I'll try to do something about it. And the way we're going to try to represent the solution is that we're going to put densities on the surface. A sigma of x, where x is element of the surface gamma, and this domain omega is our x0 domain. And we'll presume that we know something like the potential, the u or du dn is given. And we're going to say that the potential is equal to this integral of the density times the Green's function integrated over gamma. And that's going to give us this potential. So that's our setup. And the way we're going to try to deal with this kind of an exterior problem is we're going to try to solve for the densities by making sure they produce the potentials or their normal derivatives that match the given conditions of the boundary. So that meant we represented the density as piecewise constants on the surface, and we wrote down a system of equations by either collocating or using Galerkin methods. For most of today, we're going to be thinking about collocation, which is you think of alpha as the weights for the basis functions, these piecewise constant densities, and we're going to try to set up a system of equations where we calculate the density by making sure it matches test points. And so we have a density, sigma, and we'll evaluate its potential at some test point, u of x, and we'll match it to the boundary condition. Or if we're doing Neumann conditions, we would take the derivative of this. How would we go about taking the derivative? Suppose we had the way this is set up is, I know the potentials, and I calculate the coefficients of the piecewise constant representation by making sure it produces potentials that match given values at test points. Suppose this was a Neumann problem. How would I change this in order to be able to set up a problem where I calculate instead of matching the potential at these test points, I want to match its normal derivative? What do I have to do to that system of equations? What change do I have to make?
Green's function.
Yeah, so you can think of it as the Green's function. You're going to have to differentiate this potential with respect to the normal. You're going to differentiate this potential at this point x with respect to the normal. And you can think of that as being another Green's function, which is the normal derivative of the potential as a function of distance. So if we're dealing with 3D, potential dies like 1 over r. The field, the normal derivative, dies like what would you expect in 3D potential's dying like 1 over r, what would its normal derivative die as I move away from a point charge?
1 over r squared.
1 over r squared. So, but we could set all of this machinery up and we could set up a Neumann problem this way. We'll talk a little bit about those different formulations, but today I want to talk about another way of thinking about this that you use very often in 2D. That is, we're not going to deal with the piecewise constant centroid collocation. We instead, last time, we talked about another way of representing integrals, and that was using this idea of a Gauss quadrature algorithm. And I want to remind you a little bit about this. So one, I wanted to remind you about the integral equations. That was the setup. These are the integral equations. Also wanted to remind you about Gauss quadrature. And Gauss quadrature would say, I evaluate an integral by using a weighted combination of the integrands evaluated at test points. So we have these two ideas. What Gauss quadrature says, if I want to know the integral of some function of x integrated over dx, I'm going to represent it as a sum of weights and points So we're going to have points and weights, and we're going to figure out the points and weights by matching higher order polynomials. So that was the idea of what we did last time. We talked about Gaussian quadrature. We said we're going to go ahead and we can figure out where the points are. The points are the roots of a polynomial. And the weights were a solution to a system of equations. All right, that's what we did last time. All right, so today we're going to put these two pictures together, but we're going to have to go through a little bit of analysis first. So we have an integral in the top picture, and we're calculating the integral not by using points and weights. What are we doing in the top case? We're calculating this integral by assuming the integrand is piecewise constant. In the bottom case, we're evaluating the integral by points and weights. Now, the top one involves calculating integrals over lines, which you can do at the bottom to quadrature. But the question is, so we have these points and weights way of doing the integral, and we have this integral that we're representing with piecewise constant lines. It seems like we ought to be able to marry these two, and in some cases you can. But I wanted to talk a little bit about this quadrature thing because at the end of last time, there's sort of a punchline about these algorithms, and I wanted to look at them by looking at a few different functions. So we're going to look at just using this Gauss quadrature scheme, this idea of using points and weights, where the points are the roots of a polynomial, and the weights are the solution of this linear system. This is supposed to be exact for very high order polynomials. And we're going to look at the error versus order for these test functions. Now, as you look at these test functions, which are a function where x goes from 0 to 2 pi, and I want to ask you about these functions. What can you guess about these functions? What do you know about them before I start writing down the plots? Obviously, I'm picking these 5 functions because they're going to do something different with these different quadrature schemes. And I want to point at that and make one additional point, just as a reminder of what we did last time. So what can you tell me about the derivatives of these functions? Do any of them have funny behaviors when you start taking their derivatives? So what about the first one, f1? What can you tell me about the derivative of that? In particular, as we go through 0. Oh, sorry, well, x goes from 0 to 2 pi, or f1 of x is. What happens to it? Yep.
It'll be like maybe a divergent point somewhere between.
Yeah, remember the square root, you take the derivative, the derivative is something to the -1/2, which means it blows up when the argument is 0, which it will be. Oh, it's because that's. So we're going to look at some of these functions. I'm going to plot them first, and then I'm going to ask you about the quadrature for each of these ones. So here are all these functions on this interval of 0 to 2 pi. And it just so happens I picked some of them, so this one with the square root. You can see which one is the square root. Which color is it? You all see? Which one is this one that does the square root function? The one that does this, right? That's the blue one, right? Because this, it was x minus pi, and we go from x equals 0 to 2 pi, so it was, the argument to the square root was going from minus pi to pi. What about these other functions? So they all have somewhat different properties. They all look a little smoother, but there are going to be some interesting things about them, and we're going to look at just doing the quadrature algorithm. And I'm going to compare it to, this is what's called the trapezoidal rule. So the trapezoidal rule was the midpoint rule, so you use points and weights. And it turns out when we're doing something like 0 to 2 pi, we're kind of, at these endpoints, we're using a half. We can either shift around or use half weights on the ends. It's equivalent. We're going to use that particular approach to doing just the trapezoidal rule. And then we're also going to do Gaussian quadrature, because we're going to pick it for very high ordered polynomials. So trap convergence, that was the second order method. Use the trapezoidal rule, use the midpoints. We expect for all those functions it to go down. What do you expect the error for it to be as you increase the number of points? If I increase the number of points by an order of magnitude, what do I expect the error to do? If I use 10 times as many points, what's the error in the integral going to be? So again, I'm looking to see how accurately I've computed this integral for each of those test functions. And all of them behave roughly like the error is second order. I just use 10 times as many points, the error drops by a factor of 100. Right, so that's what you'd expect from the trapezoidal rule, or this midpoint rule. One of them doesn't do that. Guess which one it is?
Periodic function.
Well, so all right, two of them don't do that. One of them does worse, and one of them does much better. The one that somebody mentioned, the one that does much better is the periodic function. There's something about the trapezoidal rule in periodic functions, and we're going to come back to that at the very end of today's class. There's one that does worse. Which one is it? So let me go back and look at those curves again. Which of these curves do you think didn't get that kind of second order convergence? Which one would you expect it not to do very well with the midpoint rule?
The square root one.
Yeah, the square root one, because it has this derivative. So it's a continuous function, but its derivative goes to infinity. And so we're at the slope as you go into where the square root shows up, goes to infinity. And that even messes up a simple midpoint rule. What about before we move on? So that was the trapezoidal rule. And we don't understand why for the periodic function it does this very fast convergence. And I'm not going to necessarily give you all the details of why that's the case. But its second order convergence is sort of what we expect for all these functions. Now I'm going to try using the Gauss quadrature where we pick the points and weights to get the optimal convergence. What do you think is going to change in these curves? What are they going to look like? Are they all going to get better? So here are the Gaussian quadrature points and weights. So for this interval, you can see the points are spread out in the center and more packed together near the sides. And the weights also have this non-uniformity. So they're spread out more in the center, and they're more heavily weighted in the center. They're more tightly packed in the ends, and they're weighted less heavily in the ends. So if we take those points and weights for this is the Gauss-Legendre, and then use that, we see the following curves. Why? So obviously I didn't pick those functions at random, because you pick 5 functions out of a bag, the chance that they will produce 5 different convergence curves for Gaussian and Legendre, that's a very low probability. So I've obviously picked them very carefully. What's different about those functions that might explain this behavior? So what do we know should be true about Gauss-Legendre? How fast should it converge? Should it go like, if I increase the points by an order of magnitude, right, do I affect, is it like n squared? Is it like n cubed? Is it second order? Is it third order? Is it fourth order? Which of these curves do you expect to be like the Gaussian Legendre, based on what we talked about last time? Yeah?
The two rapidly reducing.
Yeah, these two very rapidly decaying ones, that's spectral convergence. So this is a log plot of the error versus number of points. On the log plot, the Gauss-Legendre, it's spectrally accurate, which means it has a curve that goes faster and faster and faster. And that was true for only 2 of the functions and not these other 3. What was wrong with those other 3, and why did they have 3 different convergence rates? So how did we get the error estimate for Gauss-Legendre last time? What technique did we use? Taylor series. And Taylor series counts on the derivatives being bounded. All right, now let's go look back and look at those functions. Now, all right, so maybe the square root one. Okay, so you can figure out, all right, the square root one with that cusp there, that's probably the one that's really converging slowly. But what about the others? The others look pretty smooth. Then you have to look at the analytic form for them, and you can see the game I'm playing. All right, I have x to the 1/2. You take one derivative, and you get x to the minus 1/2, and that blows up. You have x to the 3/2. You take one derivative, you get x to the 1/2. Take a second derivative, and what happens to the derivative? What happens to the second derivative for the second function? Blows up too in the interval. What about the third function? How many derivatives do you get to take before it blows up? So you take 2 and the third derivative blows up. So now we go back to these functions and you can see which is which. Square root function, 3/2 function, 5/2 function. Right? However many derivatives you have that don't blow up is the order of convergence you get with Gauss-Legendre. And if the function is infinitely continuously differentiable, you get this curve. So you get this curve and your function is really smooth. When you have a derivative discontinuity, a second derivative discontinuity, a third derivative discontinuity, and all is lost in these methods. So they're really great methods, but your functions have to be really C infinity. That is, they have to be continuously differentiable. And if they are, and the 2 functions, the one that was periodic and the one that is infinitely continuous and differentiable but not periodic, both of them have this exponential convergence. All right. That was just a reminder. Okay, so we now have a couple things. We have a method for solving these 2-dimensional integral equations by breaking the surface up into piecewise constants and then solving for the weight or how dense each of those line charges are. And we can use that to discretize in 2D and solve an exterior Laplace problem. We're going to talk a little bit about that, and we're going to compare a couple of things. Then the second thing we have is this other way of calculating integrals, which maybe we could use to calculate those line charges. And we're going to see that we can marry these 2 ideas together, but only in certain circumstances with what are called Nystrom methods. And we're going to talk a little bit about that. And I'll show you an example. And this is what you're going to do the project on Wednesday and Thursday afternoons. Is that what we're finally still on? Or evenings, rather? So we're going to have one problem set. There's also a project due, so we're not going to have your hand in very much. So please come to one of the evening sessions to do the problem set. You can probably do it there, get checked off, and then you won't have anything to hand in. So we're trying to make it so you get a chance to play with these ideas, but not put a lot of extra work on your queue. So I want to talk about trying to marry these together, and I want to talk about it in the context of thinking about certain kinds of equations. And we'll dig into this in a little more detail next week. We'll talk about some more of the details of this, but for the moment, I want to just get at this idea of the difference between first and second kind equations, and then we'll do something on the second kind equations. So here's one 1D representation of an integral equation. So I have a potential I want to solve. I know it on this integral from -1 to 1, and I want to calculate what the density is. And the density is plugged into this integral whose Green's function, if you want to call it that, is x minus x prime in absolute value. Right, so we want to calculate the density, and we're given a potential, and we want to compute the density, which we don't know. We want to figure out a density that gives us that potential on this, this unit interval. So how do we do that? Well, we do piecewise constant centroid collocation. Bless you. So the piecewise constant centroid collocation says for each of these integrals, we're going to construct a density at each of those intervals, and we're going to pick that density so that we satisfy this equation. That is, it gives us the potential at these test points. And what we have to calculate is this integral from xj minus 1 to xj of x of collocation point I minus x prime ds prime. So we're going to integrate this line integral. We need to calculate that in order to calculate what are these matrix entries. So we're going to have to calculate these integrals. How can we calculate those integrals? We need to calculate this. So how should we calculate these integrals? We've got to calculate one. We've got a bunch of those to calculate. We've got to calculate how many of these do we have to calculate, by the way. What has to be true for how many j's, for what i's, and for what j's? How many of these are going to have, so each density on each line. So the density in the jth section, it affects the potential at how many test points? So if I imagine I'm going to have to make this, I'm going to have to calculate this integral for every test point. So that's for I equals 1 to n. And how many values of j? How many different ones of these I'm going to have to do? So I take one section. Right? I imagine here's my piecewise constant collocation scheme. Here's my interval. Here's my one interval. This is the jth interval. And it contributes to all the collocation points in the problem, including its own. So I have, for each of these intervals, I'm going to have to calculate this. I'm going to have to do this for every single interval. So I've got all these integrals to calculate. I've got 1 to n for each of them. So I have how many integrals to calculate? N squared, n cubed. How many vote for n squared? How many vote for n? Oh, good. All right. Because truth is a democracy. No. Okay, so we have this system of equations that we're going to generate. And we could calculate these integrals. How are we going to calculate these integrals? Can we use the Gauss quadrature scheme for those integrals? Why not? It's just an integral. It's 1D. We know how to do it. Is there going to be a problem using the Gauss quadrature for that integral? Is that function continuous everywhere? It's an absolute value. What does it look like when you cross 0? It looks like this, right? So is that going to have infinite continuous derivatives? No. So the only term we have to worry about is the self term. All the other terms, it's fine. So we could use Gauss quadrature, or you could probably do that one analytically. Okay, so we calculate those integrals. Then we have this charge density representation. So we're representing the density with a weighted combination of piecewise constants. So we've got a piecewise constant, a density representation. We can go ahead and plug it into the integral, where we get, for this collocation discretization, we get all these entries. We have each one of the entries in the matrix takes us from one density to one potential. So we have one column for each density value. That's taking the jth density and calculating its potential at all the collocation points. We have one row for each collocation point. That's the contribution of every density to a particular collocation point. So if we imagine we have all these densities, and we have one collocation point, They all have to contribute to the collocation point. Of all these densities. So this is one row, and this is one column. So you can keep in mind those pictures. One column says one density contributes to all the collocation points. One row, all the densities contribute to one collocation. One column, one density contributes to all the collocation points. In one row, all the densities contribute to one collocation point. All right, so that's what the matrix looks like. And now we start to refine the discretization. So we have this integral. We break it up into n sections, then we break it up into 2n sections, we break it up into 4n sections, and because we're so used to this, we expect that as we increase the number of sections, the answer should get better. We should converge to the correct solution. And that isn't actually what happens. When you solve this first kind integral equation, and you refine the discretization, the answers actually get worse. Why is that? What's happening in this problem that causes that to occur? Well, it turns out that's just true of first kind integral equations generally. We're going to go back and look at that a little bit more carefully, although we're not going to focus on it too much today. But we're going to look at another type of equation. So the first kind equation is, I know the output of an integral, and I want to figure out its input. I know the potential, I want to figure out the density. There are many integral equations that come up with a different form, in which you know the potential, and the density shows up both inside and outside the integral. That is, the density shows up directly and also inside the integral. This equation is called the second kind equation. So first kind means the density shows up only in the integral. Second kind means it shows up in two ways, inside and outside the integral. So what about this equation? What's different? So we go through and we say, oh, all right, well, we'll use our piecewise constant centroid collocation method, even though in the first kind case, it produced a method that as we refined the discretization, the answers did not converge. They got worse. But we're going to do it anyway and see if it works for this kind of equation. And what we see is there's one extra piece to this, which is because the density shows up outside, as well as inside the integral equation, we see this sigma ni, the self term, showing up along with the summation. So all the rest of this looks just like the first kind equation, and the only extra piece is the sigma ni. When I write down the matrix that represents the linear system I'm going to solve to compute those coefficients, what's going to change? What will be different? So this is exactly the same matrix we set up for the first kind equation. Each column corresponds to the contribution of a density to all the collocation points. Each row corresponds to the contributions of all the densities to a given collocation point. And the extra piece that the second kind equation added to it is what? Just these ones. Right? And that's because the second kind equation had the density showing up both outside the integral equation and inside the integral equation. So what happens in this case when we find the discretization? Well, and it's really hard to see in this picture, as you increase the order, the answers get better and better. It converges. The first kind equation didn't converge. So we're going to think a little bit about how this happened now, and then we're going to try to take advantage of that. So the question is, of course, the ones you probably think of, or the ones you know, are, I know the potential and I want to calculate the density. These are the ones that often come up when you write them down physically in 3D. But there are other kinds of formulations of those problems that generate second kind equations, and we're going to do that in a moment. We're going to see the Neumann problem ends up doing that. So we need to think about what this integral operator does, and we're going to try to develop some intuition. So I'm not going to be very formal, but I'm going to try to give you some intuition about what's going on. So what does the integral operator do? When you put something into an integral, you really only get to see what's under the curve, under the curve. So the area under the curve is kind of an averaging of a function. So we might imagine that this integral operator actually takes lots of functions and produces the same output. If that were a linear system, we'd think of it as being singular, and it is true it's singular in the case of this integral operator. That is, if I imagine a function that is non-zero only at one point, and I put it inside an integral, provided the term is multiplied by, it doesn't blow up, doesn't go to infinity, then the output is 0. The area under the curve for a function like this is 0. So imagine I have a line, and then I put all these needles on it. So imagine, I don't know, imagine a porcupine compared to a, I don't know, an armadillo. One has a smooth surface. So these methods can't tell the difference between the two because the porcupine has quills, and these quills have no area under them. So from an integral operator, you can't tell the difference between a porcupine and an armadillo. I mean, you can. If you pick it up, you get stuck. But, and that's sort of the problem, is that when you look at this, you have all these functions. So if I come up with a density that satisfies my integral equation, that is, produces an output, and I also have that, so if I've got a density that satisfies my integral equation, and I also have all these densities, all these quills, if you like, that I can add to my function, and I can still satisfy the integral equation, because once I plug them into the integral, they come out as 0. It means if I've got one solution, I have an infinite number of solutions. So that's why in 1D, when we refine the discretization, we're getting this problem that when we do this collocation operation and we start to refine the discretization, we discover that we're picking up the case of the quills. So we're imagine taking an interval and making it into shorter and shorter intervals. So we're taking this interval and we're basically taking these boxcars, and when we refine the discretization, we take those boxcars and we make them into smaller boxcars. And even smaller boxcars. And as we go down in the discretization, we're getting closer and closer to these functions which are 1 point that are non-zero, the two quills. And we have lots of them, right? They can be anywhere. Right? We can have one here in the middle. We can put a quill. We can put lots and lots of them. In fact, there are an infinite number of them. So we're going to need to be in a few minutes a little bit more formal about it. And what we're going to think about is K, the operator, the integral operator, takes functions to functions. K with an underbar under it takes vectors to vectors. That's the matrix. And we're going to have to be a little careful about that, because when we do the discretization, we're going to worry about whether we're talking about the operator applied to piecewise constant representations, or actually the matrix. So let's have a look at what happens. So we're going to look at the matrix and see what happens as we start to refine the discretization. So it's a little bit hard to see here, but what's happening is when n equals 10, you have 10 eigenvalues of that matrix. That's the collocation matrix. So imagine, calculate the eigenvalues when n equals 10. Calculate the eigenvalues when n equals 20, you'll get 20 of them. Calculate the eigenvalues when n equals 40, then you'll have 40 eigenvalues. And then plot them all together. And you'll see that when n equals 10, the first 10 eigenvalues go from somewhere around 2 or 3 down to 10 to the minus 2. And then when n equals 20, it goes down a little further. And then when n equals 40, they go down a little further. And as we refine the discretization more and more, what's happening in the eigenvalues is they're going closer and closer to 0. So the more you refine the discretization, not only are the eigenvalues going to 0, there are more and more of them. So if you infinitely refine the discretization, you end up with an infinite number of 0 eigenvalues, which means the matrix is incredibly singular. So that's what goes wrong when we try to converge this problem. So what do you think happens to the eigenvalue picture when we go to the second kind of equation? What happens to the eigenvalues of a matrix when you add the identity to it? So how many of you know the spectral mapping theorem? Have you heard the spectral mapping theorem? Most useful theorem you'll ever learn. It says, if I take a function of a matrix, if I want to know the eigenvalues of a function of a matrix, it's the function of the eigenvalues of the original matrix. And that works for any analytic function, any function you can represent with a Taylor series. So if we have I plus A, then the eigenvalues of I plus A equal the eigenvalues of A with 1 in front of it. This is a function of the matrix. We're adding the identity to it. And it says that the eigenvalues of this matrix are the same function, adding 1 to it, to the eigenvalues. What happens if I add 1 to those eigenvalues? Do they go to the 0 anymore? All right, so now we have this problem. Our first kind integral equation generates a matrix that is progressively worse conditioned, and we see it because the eigenvalues are approaching 0. And the other way to see it is to think of this discretization, this progressively refined discretization, where as we increase the number of sections we're breaking the integral into, they get thinner and thinner, and they start to look like needles, like quills. These things that when you put them into an integral, you get 0 out. All right, so that's the intuition. And then the great thing about the second kind equation is it's the same operator plus the identity, which means all those eigenvalues that are accumulating around 0, what are they going to accumulate around? 1. So what does that mean about the second kind equation as you refine the discretization? Does it get worse conditioned as you refine the discretization for the second kind equation? So what are all the eigenvalues? So I keep refining and refining. Find an element, find value methods. What happens as you refine the discretization? What happens to the matrix? It gets worse conditioned, and worse and worse and worse. Second kind integral equations, what happens when you refine the discretization? The operator has eigenvalues that approach 0, and then is shifted by 1. So it doesn't matter how fine you make the discretization, the second kind integral equations, in fact, don't converge. And the way to think about it is when you have the identity plus k applied to a smooth function plus a quill, what comes out, the quill still shows up because it shows up through the identity operator. Right? So that means second kind operator, identity plus k, can tell the difference between an armadillo and a porcupine. And you have to pick them up. Right, so that simple intuition is behind why when we look at the eigenvalues of the second kind integral equation and we increase the discretization, the first 10, well, the first few are wherever they are. Then up to 10. And then the next 10, well, they're, by that point, really close to 0. And then after that, they all the operator eigenvalues are close to 0, which means the second kind operator, they're all really close to 1. So if I apply something like a Krylov subspace method to this problem, how badly conditioned is it? How fast is that going to converge? So is this an ill-conditioned matrix? Ever? No matter how fine you make the discretization? No, if it's a second kind integral equation, it's always well conditioned. Almost. There's still some issues about the first eigenvalues, and we'll talk about that in a moment. So we're going to look a little bit at this theory, and I'm not going to go through the theory in that much detail here in class. I'm going to flip through a bunch of the slides and leave the notes for you on the website. There are a lot of details about tracking the differences between what's the integral operator, what's the integral operator applied to these basis functions, and what's actually the matrix. And we're going to need to track that carefully, and I'm going to sort of wave my hands over some of those details and let you read them because it's just not that interesting to watch in class. But you can look at the details, you can go through them, but you know, it's not a good classroom exercise. So we're going to come up with three things. We have the matrix, which has a bar underneath it. We have the operator, which has nothing next to it. And the operator applied to a piecewise constant discretization with n basis functions. So we've got these three different operators. And we're going to try to do that so that we can compare the discretization of piecewise constant density to the original operator and write down the difference between them. And that's really what we're going to try to show, that we can write down, if we represent the density as a weighted combination of basis functions, where the basis functions in this case are orthogonal. Are the piecewise constant basis functions orthogonal? If I have two functions, one that looks like this, and another one that looks like the second case, a shifted pulse, are these orthogonal to each other? Is the integral of basis 1 times basis 2 equal to 0? If I take the product of these two and integrate, is their result 0? Yeah. Okay, so these are orthogonal. If I start to do rooftop basis functions, they won't be. So we're gonna assume that just because it makes it a little easier to think about how to do things like projecting. So we can project a given density onto the basis function just by projecting it onto this orthogonal basis. You don't have to set up a system of equations, you just project. Right? And once we've done that, once we've done this projection, we can then think about writing down the integral operator in terms of these projections. And this is the point where I'm going to wave my hands, because at this point you can go through the details of this, but what we're trying to do is to see some way of comparing the exact integral operator to what we get when we introduce this piecewise constant density discretization. And we're going to see that we get this projection, and we're going to have to keep track of that. But what we get out of this is that we have a representation of if we start with a density that's piecewise constant, it's a density that's defined everywhere. We have an operator that's defined everywhere. This is not the matrix. Now it takes a piecewise constant density, which is defined over space, and maps it into a potential that's defined over space, and set it equal to a set of another potential that's piecewise constant over space. These are all functions of space. We can then compare the two, and we can ask a question. So if we start with a second kind integral operator, and then we introduce a discretization so that a piecewise constant discretization, and we say that the original integral operator is solvable. Right, so we say that I plus k inverse is bounded. That means there really is a solution to the second kind integral operator. If there is one, and we also describe the discrete equivalent, that is, we introduce a piecewise constant density and come up with a discrete operator, we get these two things. If we have consistency, meaning if the continuous operator and the operator projected onto the discrete basis set, if they applied to any test density, goes to 0. That just says the two operators, the discrete and the continuous one, do the same thing as the n goes to infinity. If it goes to 0, and we do the same thing with the right-hand side, then the discretization converges. So that's all we need. Now to prove that, it's a collection of steps, and I'm not going to try to drag you through it. And it has a collection of technical points, many of which are sort of get us lost in the details. What I want to say is this, that as long as your representation of the integral operator converges. That is, it will give you the same result as the original integral operator when you refine. That is, as long as you have a way of evaluating the integral that's accurate and gets progressively more accurate, then the density will converge. And the accuracy with which you represent the integral operator, the rate within that it converges, will be the same as the way the density converges. So what does this mean? So I didn't take you through the details. It says that if I have a second kind integral equation, and I accurately compute the integrals in the second kind integral equation, that's all I have to do. As long as I've computed those integrals accurately, I will get convergence, and the rate at which the thing will converge is dependent entirely on the rate at which the evaluation of the integral converges. With that in mind, what method should you use to evaluate the integral?
Quadratic.
Yeah, the Gauss quadratic. Because that gives us exponential convergence. That means if we're solving a second kind integral equation, we should get exponential convergence for the integral equation. All right, so this is the thing about second kind equations. This is what is so amazing about them, and why for years they were very popular until the problem with the dense matrices they generated became an issue, and then we switched to methods that produce sparse matrices. And now we have other methods for sparsifying B's, so we use them again too. But let's try this out. Right, so this is what we're going to do. We're going to say we have an integral equation. We have a second kind integral equation, and we're going to apply a quadrature to the collocation equation. So here are my collocation equation. Here's my test point, xi, then my Green's function, my unknown density, and we're going to replace this integral with a quadrature approximation. We have the evaluation points, x prime gets replaced by xj, the weights for that quadrature point, and remember xi is the collocation point. So all we did was to say, let's do the integral equation. Let's say we don't know what the density is, but we can write down what that integral operator is using a quadrature scheme. So can I just solve this? Well, I got two things. I need the density at the collocation points, and I also need the density of the quadrature points. Then I only have, so I can pick with n collocation points, I can get n equations, but I have two n unknowns. The density of the quadrature points, which I have n, and the density of the collocation points, which I have another n. So what should I do? Where should I put the quadrature points? So suppose now I decide I have this surface. I have the density on this surface, sigma of x, and I'm going to calculate, and I know the potential. I know the potential psi of x for x elements of the surface. And now I say that the potential at x is given by the density at x plus this integral of some g of x comma x prime of the density of x prime integrated over this gamma. Now I say I'm going to replace this with a quadrature representation, a sum of wi's g wj, so g of xi comma xj sigma of xj plus sigma of xi is equal to the potential at xi. So I'm picking a particular point, sigma of xi, and I'm saying now we're going to pick these quadrature points to evaluate the integral. And the problem is I have all these test points and all these quadrature points. So for each of my collocation equations, of which I have n, And for each of my quadrature points, j equals 1 to n, I have n equations in 2n unknowns. How can I fix this? How can I get it so that I have only one set of equations? Or one set of unknowns? I have one set of equations. How do I get one set of unknowns? Yep.
You can make the cluster points coincide with the.
No, you can't. You want to put the quadrature points in. You want to make the quadrature points and the collocation points be the same points? Yeah, but how do we pick the collocation points? What was the rule for picking the collocation points? We had a rule for picking the collocation points, didn't we? Well, we had this idea that if you broke it into piecewise straight sections, you should pick the midpoint or the end point or something like that. All right, maybe it's okay. After all, I didn't have a very good way of picking the collocation points. Why not make them equal to the quadrature points? If we do that, what do we get? If you did this in somewhere in the 1800s, you get to name the method. So if you say, we've got these collocation points, we've got the collocation points and the quadrature points, and they're the same. If we set them equal to each other, you get a method that's referred to as the Nystrom method. We just go ahead and say, we'll use as the quadrature points, we'll just make them the same. So we're going to co-locate the quadrature and collocation points. Because we didn't have a very good way of picking the collocation points anyway, why not make them the same? It gives us a set of n equations and unknowns. If we do that, we're still evaluating the integrals spectrally accurately. And what does that mean is the convergence of these methods? So here's the other thing, right? So the first time you tell this to a student, so I used to give out a problem set where everybody would have to calculate these line integrals, and then I'd show them Nystrom methods and say, well, look, you know all that time you spent doing those line integrals? Well, that was a waste of time because you just did the Nystrom methods, in which case you only need points and weights. And oh, that would make people furious. So I stopped doing it. Well, yeah, it's good for you to calculate integrals over lines, although maybe not that good for you. But not only is the method spectrally accurate, the piecewise constant collocation, this is at best a second order method. The Nystrom method, it's spectrally accurate. That means when we refine the discretization and we look how well we're converging and compare it to piecewise constant collocation, we get, right, so we'll get a method because of the spectral accuracy of our representation of the integral operator because of that theorem. We'll get something that converges spectrally accurate. So here's a Nystrom method applied to an integral equation. And we're looking at the top curve, which you can barely see it in the curve, is the piecewise constant collocation scheme. We broke it up into 4 through 11 intervals. And then we did the Gauss quadrature Nystrom method. And by 11 intervals, we're almost at machine precision for the Nystrom method. And for the piecewise constant collocation, we barely got the error down to 10%. But I did something here and made it different than the original Green's function. What did I do? Why is this Green's function different from the one I started the lecture with? Remember the one at the beginning of the lecture, what Green's function it was? It was x minus x prime in absolute value. And now I've changed it to be x minus x prime squared. Why did I do that? Because the curve with absolute value, that has a discontinuity in it. And when you have an integral with a discontinuity in it, what's true about Gauss quadrature? You lose the spectral convergence. Right, so I used a little sleight of hand to get this comparison. I picked the example very carefully. So the question is now, is that a practical method? So we now have this Nystrom method, which has exponential convergence. And the answer is, if it has exponential convergence for non-singular kernels, why don't we use it always? Why don't we teach you anything other? Why did I start this lecture with the first overview where we talked about panels and integrating over panels? It's because most physical problems of interest have singular integrals, singular kernels. 1 over r, e to the kr over r if you're doing Helmholtz problem. So if we're talking about potential flow, or most of the physical problems, we're interested in Laplace's equation, Helmholtz equation. Most of the ones, the PDEs have integral, have kernels, the thing that goes inside the integral, that do have singularities in them, which means these Nystrom methods don't work. Well, so we're going to stop here, and then I'm going to talk a little bit about one particular case. And I'm going to show you a little bit of the details of this in order to give you a sense of the fact that there are interesting integral operators that do, for which this is the case. And we'll do this as part of the project. So when we think about trying to solve an integral equation, imagine in 2D, bless you, we're trying to solve a Dirichlet problem. So we imagine that we know the potential at each point x, and it's given to us by an integral of now the 2D Green's function. I'm just going to write it as x prime and sigma of x prime d gamma. So we're going to think of this as we have Laplace's equation outside, and we want to know the density, and we know the potential on the surface. And we're trying to solve this problem. This is the Dirichlet problem. So what kind is this? Is this first kind or second kind? So this is first kind. So we're not going to be able to use our Nystrom method for the first kind equation because, one, it's only the second kind for which we have that theory about the integral equation solution picking up the same asymptotic behavior as the, or same accuracy as the quadrature. So we can't use it for a first kind equation. So we're not going to be able to solve this Dirichlet problem. What about a Neumann problem? Suppose I have the same interval, the same equation, and instead I have partial psi partial n is given, and x is given. What's the integral equation I write down then? Well, it's still true that the potential is given by this Green's function multiplied by density, except I don't know what this is. So how can I turn that equation into one that I can use for the Neumann problem? What could I do? So here's my Neumann problem.
Just differentiate the whole thing.
You could differentiate the whole thing. All right, so let's differentiate the whole thing. So we're going to calculate d by dn of psi of x. And we're going to note that this is the n of x. And we're going to keep track of that because we're going to need that in a moment. So is that helping us all? What is this thing? Can I pull the dn dx inside the integral?
Yes.
Can you?
The integration's over a different variable.
Say again?
The integration's over a different variable, x prime.
the integration is over a different variable, so can I pull that inside? If I do, what does it mean? Right? So I can pull that normal derivative inside, but then what happens to it? So now, let's imagine what that potential looks like, and see if we can think out what it might look like. So I might expect that if I write down the potential as I approach a density, so I want to know what the potential looks like as I approach this density. What do I expect the potential to look like as I approach this density? In 3D, it's easy to think about. So let's think about it in 3D. And we can get some intuition from 3D, and then I'll stop there and we'll do it a little bit more precisely at the beginning of next time. What do you think it would look like in 3D? So remember that I have this density, and now this potential is equal to the integral of that density, x prime, divided by x minus x prime in absolute value, integrated over some short interval, say x1 to x2. If I plot this potential, now let's use a different variable here, r, where r is, we're just going to look at the potential on this line r. And where r is equal to 0, that's where this line is, although if we're thinking about it now in 3D, that's not a line. So here's my charge panel. And I'm looking at the potential as I approach this line. Yeah, and you went off that time, didn't you? So we're approaching this charge, and then we're coming out the other side. If I plot that potential, what's it going to look like? So suppose it's a positive charge. Then if I hold it this way, so on the right side, what's the potential going to be? Is it going to be positive or negative? If it's positive charge, I'm looking at the potential as I move away from the panel. Is the potential positive or negative? Positive. If I'm looking on the left side and I plot the potential, what's it going to do? Is it going to be positive or negative? Positive. And in both directions, it's going to do what? Go up or go down? Down. Right, so this is, again, in 3D, this is what the potential is going to look like. It's not going to blow up as we actually approach this charge density sheet. That we proved the very first lecture by calculating out a hole in it. So if that's a plot of the potential as you approach the surface, what does the derivative of the potential look like? So what's it going to do is, as r is increasing, as I approach the panel, as r is increasing, what's happening? The potential is increasing. What happens to its normal, the derivative in the normal direction? Now I have to pick which direction is normal. So let's say the normal direction is in the positive. What happens to this? So this is the normal. So what happens when I take the derivative of this potential in that normal direction? Is it increasing or decreasing? Is it going? So now I have to be a little careful. So we're talking about perturbing it in the normal direction. Right? So we're going to ask, what happens when we look at the derivative potentials and point a little bit in the normal direction? So we're going to take the difference between the two. So if we look at that, it looks like it goes up. The slope here isn't infinite. Right? It goes to some finite value. Then what happens after we cross the axis? There's a jump. How big is that jump? So we're going to do a little bit more with that next time. So I hadn't quite. I'm sorry. I glossed over a few too many details in the derivation of the convergence theory for the second kind of equation. I'm going to stop a little earlier, but I don't want to go any further than this. But I want us to ask this question. If I calculate this derivative, it has to have this jump in it. How big is that jump? What's it going to be proportional to? Yep.
The charge, the surface charge.
Yeah, it's going to be proportional to the density. So what do you expect this thing to generate for you? So you have this jump, so we're on the other side of the jump. The density is going to show up. So you're going to have some alpha times the density plus an integral of this derivative. What kind of equation is this? First or second kind? It's second kind. All right, so I'm going to pick this up next time because I need to get this far. And now, to have you hang on to it, I need to have some slides so you can see the pictures in a little more detail. It's too hard to decipher it from my chalk writing, but I just wanted to give you the sense of this. So what we're going to do next time is we're going to pick up from here. And we're going to look and see if we ever get second kind equations that we can use this Nystrom for. And we're going to see that Neumann problems generate second kind integral equations. And those Neumann problems generate second kind integral equations we can solve with Nystrom methods. And then we'll end up looking at this issue of what happens when we generate those kinds of matrices and the fact that they're dense, and we can figure out something to do with those two. So we're going to pick this up next time, but I want to give you this idea that we have this quadrature scheme. When we use this quadrature scheme in integral equations, we can come up with this Nystrom method, but the Nystrom method counts on a kernel that's smooth and a second kind integral equation. And the ones you naturally write down, the Dirichlet problems you naturally write down with Green's functions having to do with PDEs, are not second kind equations, and they don't have smooth kernels. But I'm going to show you that if you're solving Neumann problems, you can do it with, you can generate a second kind equation, and in 2D, you get a smooth kernel. And to see that, we're going to need a little bit more time. So let me stop there, and we'll pick it up next time. Let me remind you that we're going to do some evening class hours, Wednesday evening and Thursday evening. If these don't fit with your schedule, complain, because we'll make a next one. Yep?
Wasn't it Monday, today and Wednesday? Was it?
So we kind of shifted it around, I think, a little bit. Which did we end up with? So,
It is Wednesday and Thursday.
yeah, I think we talked about, if it doesn't work for you, we'll do another session on Monday. The problem is, we can't really have something else due other than the project that next week. So there are rules about what we're allowed to do in the last week of classes. But if you can't make the Monday or Wednesday or Thursday of this week, we'll make a session on Monday next week. So anybody who has a conflict, if you can't make one of those days, that's on us. You just let us know and we'll make an extra session. And the idea is to try to make this so it's a good experience for you and so that you can try some things out, not to add another thing to your queue of many end of term duties. So please, if Wednesday and Thursday turn out to be problematic to you, and problematic means you have a Friday problem set due, or anything in that range. Any reason you want to push it off to the following week, we'll accept. So we're not, this is for your convenience, not to be an extra thing. All right, we'll pick this up next time. Yep.
So when are evening classes?
Say again?
Which days do we have evening classes?
Say again?
Which days in this week we have evening classes?
Oh, so we'll have them Wednesday and Thursday. It's on the website. It's Wednesday evening and Thursday evening this week, and we'll do a replacement session Monday evening of next week. And we'll put another one if that doesn't solve it for everybody.
Okay, and it's here?
Yeah, we'll do it here.
7 to 9?
Yeah.
It's 7 to 9. And we'll get it posted, we'll make it clear, we'll post it again on the web. I think we talked about a few different alternatives to do this. But if you make sure it's up on the
Yeah, it is actually on
It is, okay.
Okay, and there is people who are requesting doing the final project in console. So if you are interested, can you just email me? I just need a count of how many students, so I know like how many simultaneous sessions I need to get on the console license. All right. Thanks.
Oh, maybe it is, yeah, no, it's been the past. Yeah, that one actor was a whole time. This one, the other one doesn't. Sorry, that was a good ending. I realized I ended early, so I didn't know. So in 3D and for the potential equation, it isn't true. That is, if the kernel is singular, the first kind of equation isn't necessarily, doesn't necessarily generate this singularity of this rate. It's only true for smooth kernel. So formally, this is one of the problems teaching this material is that for smooth kernels, the theory is very clear. But none of the problems of interest have smooth kernels at all, singular kernels. And for the cases, everything's on. So in 3D, you can do first kind equations because the kernel is singular enough. It's like imagine if you have an impulse inside a signal, it pulls out the density inside the signal. So if the singularity is strong enough, it's almost like having a second equation. So first kind 3D equations are still get worse condition as your final discretization, but very slowly. But second kind 3D equations have a boundary condition. But it is true that the first kind equations are better conditioned than 3D because of the singularity of the kernel. So of course it's no problem. You can solve those problems in 3D. And you can in 2D, or it's harder in 2D because the singularity isn't quite as strong enough to give you that same, it still can be solved. You can still do second kind.
Exactly.
It's just you do get a it's worse than 2D.
Oh, yeah, that's
In 3D it's very slow.
that's nice.
Singularity, I mean the derivative near the singularity has to be equal.
Yeah, so the way to think about it is, if the Green's function actually has an impulse, then an impulse inside an integral, when you integrate an impulse, you just get the second kind. It gives you a second kind of argument.
Okay.
So if you write down the Green's function as impulse plus smooth, then you get exactly the second kind.
So in 3D, it just essentially becomes the impulse function because it's like a 1/.
Yeah, not quite. I mean, it's not quite as good as an impulse. Impulse would be truly second kind, and you get bounded dimension number. It's sort of almost an impulse. It's like a square root of an impulse. So you get the square root of the condition.
What was the rate it goes to single in the case you showed? I mean, you
Listen.
showed on the semi-log plot, but if you show it on the log plot.
Well, it went down slowly because the one I picked as an example was the absolute value one.
I see. Oh,
And
okay.
because it's a non-smooth kernel, it doesn't go down that fast. If I'd used the x minus x squared kernel, it would have gone down faster. And I keep meaning to redo those results, and I keep forgetting to. It was one of the things that so that particular case that I used, where you see the slow approach to zero, it would approach much faster than that, but it's still not that fast. I mean, it's still, but it is fast enough, and it depends on the singularity. So if it's completely smooth, it would go down exponentially fast to zero. But with a first derivative discontinuity like that, it goes down slowly. And if I had, if it was smooth in the first derivative, then it would go down even it would go down even slightly. The smoother it is, the faster it goes down. So we were looking at, if I had a discontinuous kernel, then it would go down even slower. But so I picked, unfortunately, as an example, the slowest one. I just wanted something that looks sort of like the operators they were looking at, and also to mention the thing about it's not something you can do Gaussian quadrature for, because that's the other important thing, is the kernel has to be smooth to use the Nystrom method.
Cool. Yeah.
Well, so we'll do this next time, and I'll do a little on the FFT, because I saw you put it in the problem set, and I'll try.
Does this make sense though? What I was thinking was solver.
Yeah, no, you do an iterative solver and you do the FFT.
Yeah, you do an iterative solver, and if you choose the equal weights, it's going to be a circular matrix.
Yes.
So I thought that you can decompose the circular matrix with the FFT matrix.
Oh, no, what you said is exactly right.
Ah, okay, cool.
Yeah,
I was just wanted to verify.
No,
that
no,
I'm saying
I
it.
think your
Yeah.
point was well taken, and having them discover that on their own with some hints at the beginning of class sounds like